Our final speaker this evening is Kathleen Fisher. She is professor and chair of the Computer Science Department at Tufts in the School of Engineering. Computer science is currently the most popular undergraduate major at Tufts and still growing. So I know most of you probably remember international relations used to hold that spot, but no more, computer science. Before joining Tufts, Professor Fisher was a program manager at the Defense Advanced Research Projects Agency, or DARPA. She was a consulting faculty member in the Computer Science Department at Stanford University and a principal member of the technical staff at AT&T Labs Research. Professor Fisher is a fellow of the Association for Computing Machinery, the world's largest scientific and educational computing society. She's a program chair for PLDI, its flagship conference on programming languages. In addition, Professor Fisher has long been a leader in the effort to increase diversity and inclusion in computer science, and she's really a champion of bridging differences and encouraging dialogue on campus. I've had occasion to attend a number of after-hours events where students are there, and where one of the main purposes is to increase dialogue across faculty, staff, and students. And often I'll find Professor Fisher there. So she has a keen interest in our students and our faculty and how we build our community. Professor Fisher received a bachelor's degree in math and computational science and a Ph.D. in computer science from Stanford University. Her research focuses on advancing the theory and practice of programming languages. All of her work is collaborative and most of it is interdisciplinary. She seeks to solve problems by developing domain-specific languages, which she's going to talk to you about, and using programming language techniques, producing software that is difficult to hack, which, whether you know it or not, is really important to all of us. In her talk tonight, Professor Fisher will describe why cybersecurity for cars and other Internet of Things devices is so difficult, and how expertise in programming languages can foil the hackers. And any of you who read the New York Times the last couple of days, there was another major article on this very topic. So a particularly special part of this final talk is the fact that Professor Fisher has brought with her her PhD student, Sam Lasser. He'll join Professor Fisher at the end of her talk to describe his work in developing technology that allows systems to throw away malicious messages from adversaries before they enter a car's networks. I wonder if they could do that for my email. So we're very pleased to not only welcome Kathleen Fisher, but also her student, Sam.
Thank you very much. Okay, I'm going to give you a chance to exercise your imagination. So close your eyes. Now imagine you're driving down a highway, maybe Highway 64 near St. Louis, and you're in a Jeep Cherokee. And as you're driving, all of a sudden, out of nowhere, the air conditioner starts to blare at you. And while you're kind of puzzling, like, why is the air conditioning going? The radio turns on full blast, a hip-hop station that wasn't your choice. And when you try to turn the dial to change it to a different radio station, or push the power to turn it off, nothing happens. And then the windshield wipers start going, and the windshield wiper fluid starts going. And then, as you're starting to climb up an overpass, the transmission cuts out. You push the accelerator all the way down to the ground. Nothing happens. You look in the rearview mirror, and there's a semi that's coming up behind you, honking the horn because you're slowing down as you go up the overpass. You can open your eyes now. All of that actually happened to Andy Greenberg. He was a Wired magazine reporter. So he kind of knew what he was getting into when he got into this Jeep Cherokee, because colleagues, or white hat hackers, Charlie Miller and Chris Valacek, had hacked into this car and made it so that they could take over remote control and completely operate the car while he was driving. Now, why is that possible? So it turns out modern automobiles are really computers on wheels, networked computers on wheels. A typical car these days has somewhere between 30 and 100 embedded control units. But an embedded control unit is just a computer. They're of varying size. Some of them are small. Some of them are fully powerful, running Linux or Windows. And they all talk to each other on the car. But they also talk via networks to other systems. And basically all of the functionality of the car is under software control for really good reasons, right? You want your brakes to be under software control because that's what enables anti-lock braking, which is super helpful. right? The fancy cars that can park and steer themselves, those have steering under software control. The key fobs that cause the doors to unlock, that means the locking is under software control. Like, basically, all of these things are under software control, and they provide lots of convenience or safety features. So we want them to be under software control. But because they're under software control, they are vulnerable to being hacked. And one of the other features of modern cars is that the software on the car talks to software off the car. So Charlie and Chris hacked the Jeep Cherokee, but earlier work by Yoshi Kono at the University of Washington and Stefan Savage at the University of California, San Diego, they showed how to hack into another car, and they showed, in fact, 5 different ways that they could hack into a car. They could hack into a mechanic's laptop, and when the mechanic plugged in the laptop to the diagnostic port that's required by law to be under the steering wheel, they could transmit the infection into the car so that they could control the car. They could hack in through the Bluetooth interface, which is what your cell phone is using to talk to the car. They could hack in through the telematics unit. So the telematics unit is the thing that calls 911 if you get into an accident. It's like OnStar for GM, but like all of the major car manufacturers have these kinds of systems. And that telematics unit means your car has a cell phone number, and the attackers can call the cell phone number and then have their computer talk to the computer that answered the phone on your car. That's the technology that Charlie and Chris used to hack into the Jeep Cherokee. And then the entertainment system is another way that you can hack in. So Stefan and Yoshi hacked a version of one of Beethoven's symphonies and burned it on a CD that played fine in the stereo in the lab, but at home. But in the car, it exercised what's called a buffer overflow error that allowed the attackers to rewrite the software in the car and, again, take over remote control. So you can see a picture here of a Jeep Cherokee sitting in the ditch. This is, in fact, the Jeep Cherokee that you were just imagining yourself being in that was, taken over by hackers. So why is this so hard, right? It turns out that security is hard because to get it right, you have to get absolutely everything right. Well, think about your house, right? If you want to make it so your house is secure from an attacker, you have to lock the front door, and the back door, and the side door, and the storm doors that go to the basement, and all the windows. And you have to make sure that there isn't a key under the mat that somebody can get into, and that your neighbor doesn't have a key that they give to somebody else, right? There's just many, many things you have to get right to protect your house. Well, it turns out it's exactly the same thing with protecting your computer. You have to get everything right. So you have to design the software right in the first place. You have to write down the specification in a way that's clear and correct. You have to implement it correctly. You have to configure it correctly. The users have to use it correctly, right? And whenever you get users involved, it's kind of game over for correctness, right? Passwords, right? You have to get passwords right. And you know, how many people think they get passwords right on a regular basis, right? Super complicated. In addition to all of these problems, we have the problem of misaligned incentives, right? The people who write the software, not so much for cars, but for computers, they don't pay the price when there's a vulnerability in their code that causes somebody to be able to break into a system and steal information or steal money, right? It's the company that's running the software that has to pay that price. And so the car companies really can't afford to add security to their products unless the whole industry adds it together, because they can't charge more for the car that is more secure than the car that's less secure, because they can't explain to consumers what difference they're getting. Right? And then the software companies have no incentive to improve the quality of their software because it doesn't matter. Like, people are buying the software anyway. So the misaligned incentives are a really key part of the problem with cybersecurity. So there is hope. It's not completely hopeless. So I'm going to talk about implementation errors, just one of the things you have to get right, and a key technology that shows real promise for making implementation be more correct. And what is that key idea? It's this thing called formal methods. So the hypothesis is that if we correctly apply formal methods to the software that we're producing for vehicles and other kinds of secure, sensitive systems, we can eliminate the vulnerabilities from the implementations, and thus rule out whole classes of attacks that hackers are currently using. So, okay, formal methods. What is this, magic pixie dust? So formal methods are mathematical-based techniques that you can be used to apply to reason or think about, prove properties about software or models of software, hardware, models of hardware. And those proofs can be checked by a machine. So it's like when you're doing your geometry proof in 10th grade, there's a system that will go through your proof and check every single line. Did you get it right? Did you get it right? Did you get it right? And if it doesn't, it will say, go back, you have to start over again. Right, so formal methods are tools that allow you to reason about code that's running in your automobile or other systems, and it will tell you whether you got it right or not. And the rightness is whether or not it's correctly implementing a specification. And it turns out if you correctly implement a specification, the odds that there's errors go way down. So some evidence for this. So right after I joined Tufts, I had the opportunity to go to DARPA as a program manager. So DARPA is the mad scientist branch of the Defense Department. It's charged with thinking over the horizon. Where is there strategic surprise that we can either leverage or avoid being surprised by if it comes from our adversaries? So I went to DARPA. Tufts was very happy to send me to DARPA for 3 years, and I was really pleased to be able to get the opportunity to make a huge difference on the national and international scale. So what we did was we tested this hypothesis. Could formal methods produce vehicles that were much harder to hack into? So we started with this vehicle here, which is a quadcopter. You can buy it from Amazon. And at the beginning of the program, we had a world-class team of hacking experts, a red team, work to break into the system. Could they break in and take over control? Turns out, off the shelf, absolutely no problem. Super easy to break in and take over control. Really, the designers had no intention of making it hard, so that wasn't surprising. Then we had the blue team, which are the researchers in formal methods, and a bunch of researchers from other fields worked on updating the software, changing it, rewriting it, proving properties about it, architecting it for security. And at the end of 16 months, they had to give it back to the red team. Now, the red team had full access to that entire process. They participated in the design decisions. They read all the documentations. They had full access to the code. So they knew as much about that quadcopter as you could imagine knowing. So a model for an adversary that was super well informed. And after that, they had 6 weeks, and during that 6 weeks, they were not able to break in and take control of the quadcopter. Not able to. So my colleague at DARPA at the time, who was an expert in this kind of penetration testing, his assessment is that that UAV was the most secure UAV on the entire planet, which is kind of scary if you think about what UAVs do on a regular basis. Of course, those are much bigger UAVs. So in the next 2 phases of the program, my colleagues worked on taking those same ideas and applying it to a full-fledged helicopter. This is a picture of Boeing's unmanned Little Bird, and we had the Boeing aviation engineers take the formal methods techniques and apply the tools and techniques to the quadcopter. So the formal methods engineers did not have access to this helicopter because this helicopter is ITAR restricted, it's proprietary. Only the Boeing engineers actually knew what was going on. So here was a case where the formal methods engineers were able to transfer their ideas so that aeronautics engineers could apply them to this helicopter. And at the end of the program, the red team was again allowed to attack the helicopter. So in fact, there was a partition set up on the helicopter, so the red team didn't have to get on in the first place. It was already code running on the helicopter, and they were charged with disrupting the operation or disconnecting the system from the ground control that was communicating via wireless connection. And the DARPA was so confident of the result that they allowed the red team to attack the helicopter while it was in flight with test pilots on board, right? So obviously nothing bad happened. The expected result happened, which was the red team was unable to break out. They could crash their own partition, which just the rest of the system was like, oh, look, the camera partition, which is where the red team code got to go, went down again. We're going to restart it. The camera would go down for 10 seconds and then come back up again when it was detected. So this is really exciting. And the goal here is to create a virtuous cycle. And what do I mean by that? So originally, you have the defense contractors, the companies that are building the software for military kinds of systems. If you went to them and said, you have to use formal methods to prove this part of your system is correct, they would come back and say, oh, come on, that's ridiculous. Nobody knows how to do that. If you put that requirement in these documents, you will not get the system. But now, with the result from Hackams, the procurement officers in the Pentagon can say, these grad students did it. Why can't your engineers? Right? So the procurement officers can put those requirements into the call for proposals, and then the defense contractors can build the capacity, because we do know how to do it, and there are people who know how to do it. They build the capacity, they bid, they win the contracts, they build the systems, and now they have this capacity that they could use for other things, like pacemakers and insulin pumps, which would also be excellent candidates for using this kind of technology, because those are also network systems. Right, so the John McCain National Defense Authorization Act, which is the authorization bill for the military to spend money this year, actually specifically mentioned this program from DARPA directing the Pentagon to explore using these kinds of tools and techniques to secure military systems in the future. So here at Tufts, we are working on similar problems. So one of the vulnerabilities of these kinds of cars is they communicate with systems they communicate with computers that are not on the car, right? So the Charlie Miller and talking through the cell phone connection. So here are these kind of purple diagrams, or these are packets or messages that are being sent from the outside world telling the car important information. And if they're purple, they're coming from an authenticated good source. But an attacker, like Charlie or Chris, could insert malicious messages. And if those malicious messages get to the car, they have the opportunity of taking over the car and causing bad things to happen. So what we're working on is creating an application-specific firewall that lives at the boundary. And what it does is it checks each message as it comes in, and if it's not the appropriate form, it just drops it on the floor. And we prove that the parser itself has no vulnerabilities, so the parser cannot be exploited by the bad guy. That's the work that my student Sam Lasser is doing, so I'm going to invite him to come up and join me and tell you about the work that he's doing.
Thanks, everyone. You might still be thinking about Kathleen's car hacking scenario from a few minutes ago. Well, I came to Tufts because I wanted to help prevent those kinds of scenarios from becoming reality. Before that, I spent some time in an industry setting, and one of the things that I learned from that experience is that the world is just full of buggy programs. After a while, I wanted to learn about and also develop new techniques for writing software that meets a higher standard of reliability. Kathleen and other computer scientists at Tufts were doing research in this area that I thought was really exciting and innovative. And that's how I ended up working on the project that I will describe next. Kathleen and I are building a filter that can protect your vehicle from the kinds of malicious messages she described earlier. And we're using formal methods to guarantee that this filter works correctly 100% of the time. The technical name for this filter is a parser. And you can think of a parser as being kind of like a grammar maven. It knows all the rules of some language, and it can figure out whether any sentence is grammatical in that language or not. I'm showing you an example in which the language is English. But most real parsers understand a language of numbers. So you can imagine that the words actually stand for numbers. The parser in this example is able to figure out that time flies like an arrow is a grammatical sentence, and so is fruit flies like a banana. It's also able to figure out that the other two sentences up here are ungrammatical because the words appear in the wrong order. So that's how a parser works. Let's talk about what happens when it doesn't work. There are two basic types of mistakes that a parser can make. First of all, it can give the thumbs up to an invalid sentence. That's called being unsound. And the first parser you see on this slide is unsound because it accepts the sentence, time flies an arrow like, even though it's ungrammatical. The second type of mistake is that it can give the thumbs down to a valid sentence. That's called being incomplete, and the second parser that you see up here is incomplete because it rejects the sentence, time flies like an arrow, even though that sentence is grammatical. Well, I have some good news to report. Kathleen and I recently built a parser, and we proved that it's both sound and complete, so it will never make the types of mistakes that we saw in the previous slide. We did this work using a tool from the formal methods world called an interactive theorem prover. And there are three main steps that are usually involved in using this tool. First, you write a program, which in our case is the parser itself. Second, you write a definition of what it means for the program to be correct. So our correctness spec says that the parser should be both sound and complete, although we have to express those ideas in very precise mathematical language. Finally, you write a proof showing that the program satisfies its spec. Now at that point, the interactive theorem prover checks your proof, and if there's a mismatch between the program and the spec, or if you've made a logical mistake in the proof, the tool flags your mistake. And because our proof passes the check, anyone who uses our parser can sleep soundly at night knowing that a malicious message can never slip through the filter. So we still have more work to do. We plan to optimize the parser so that it runs faster. And we'd also like to apply these same verification techniques to a whole suite of parsers that are tailored to different applications. But the work we've already done brings us a step closer to our goal of building software that's truly guaranteed to be reliable and secure. And with that, I'll turn it back over to Kathleen. Thank you.
So the work that Sam is doing is not all the work that Tufts is doing in cybersecurity and policy. I talked to you earlier about how the incentives weren't aligned properly for solving security problems. And that really reflects that cybersecurity is not just a technical problem. It is a technical problem, but it's also a policy problem. It's a legal problem. It's an ethical problem. And so we need to have more broad investment in cybersecurity than just like the technical side of the computer science department. And Tufts is in fact doing that. So we recently hired Susan Landau, who is a bridge professor. She's 50% in computer science and 50% in the Fletcher School. In fact, Fletcher has just hired another professor who does cybersecurity and policy. We also have partnerships with ANS, where Ming Chow, who is in the audience somewhere, and Jeff Taliaferro, who is a political science professor, co-teach a class on cyber warfare. And the goal is to, and we're exploring creating a new master's in cybersecurity and policy with the goal of growing a new population of students who understand both the technology and the policy, so that we can have technical people who speak policy and policy people who speak technical, so that we can have policy that is informed by the technology and technology that informs the policy. So we get a really good synergy. And with that, I will stop and take your questions.